Hello everyone, here in this section we have directional derivatives and gradient vectors. The rate of change of f in the direction of u at the point p naught, and here we have x naught, y naught, is the rate at which f changes along this line at p naught. So here we have this direction and it's increasing. Definition: the derivative of f at p naught in the direction of the unit vector u equal to u sub 1 I plus u sub 2 j is the number. The derivative of f with respect to s in the direction of unit vector u at the point p naught is given as the limit as s approaches 0 of f of x naught plus s times u sub 1, and u sub 1 is the I component of unit vector u, comma, y naught plus s times u sub 2, and u sub 2 is the j component of the unit vector u, minus f of x naught, y naught divided by s. Using the definition, find the derivative of f of x comma y equal to x squared plus x times y at this point p naught 1 comma 2 in the direction of unit vector u equal to 1 over square root of 2I plus 1 over square root of 2j. By definition, derivative of f with respect to s in the direction of unit vector u at point p naught is given as limit as s approaches 0 of f of x naught plus s times u1 comma y naught plus s times u2 minus f of x naught comma y naught divided by s. So here u sub 1 is the I component of unit vector u, and u sub 2 it is the j component of unit vector u. And this is equal to limit as s approaches 0 of f of your for x naught we have 1 and y naught it is 2. So here we have 1 plus s times u sub 1 it is 1 over square root of 2. So comma 2 plus s times 1 over square root of 2 is what we have for u sub 2. And then minus f of 1 comma 2 then divided by s. And this is equal to limit as s approaches 0. Here using what we have for f of x comma y. This is x squared plus xy. So this part it is x and here we have y. So we have 1 plus s over square root of 2 squared plus 1 plus s over square root of 2 times 2 plus s over square root of 2 minus, now for this part, f of 1 comma 2 here, x is 1, so here we have 1 squared plus, then we have x times y, so that's 1 times 2 divided by s, and this is equal to limit as s approaches 0. So for the first part we have here, this is equal to 1 plus 2 times s over square root of 2 plus s squared divided by 2, and here for this part multiply, so that is equal to, we have 1 times 2 it is 2, then we have 1 times s over square root of 2 plus 2 times s over square root of 2, so that is 3 times s over square root of 2, then plus multiply these two, so here we have s over square root of 2 times s over square root of 2. So here is s squared divided by 2. And then for this part we have 1 squared plus 1 times 2, so that is 3. So subtract 3 and then divide by s. So now here simplify, this is equal to limit as s approaches 0. Here on top numerator we have 1 plus 2, then subtract 3, so that part is 0. Then here we have 2 times s over square root of 2 plus 3 times s over square root of 2, so that is 5 times s over square root of 2. This part we have s squared divided by 2 plus s squared divided by 2. So that is equal to s squared. Then divide by s. After dividing by s, here we have limit as s approaches 0, 5 over square root of 2 plus s. So this is equal to 5 over square root of 2. So the rate of change of f of x comma y equal to x squared plus xy at p naught, which has this point 1 comma 2 in the direction u is 5 over square root of 2. The slope of a trace curve C at P naught is limit as Q approaches P. So slope PQ, this is the directional derivative. So here we have derivative of f respect to s. The direction of unit vector u at point P naught. So this is equal to directional derivative of f at this point P naught. Definition: the gradient vector or gradient of f of x, y at the vector. So here we have gradient of f is equal to partial derivative of f respect to x, I plus partial derivative of f respect to y, j. The value of the gradient vector obtained by evaluating the partial derivatives at the point p naught. So x naught comma y naught is written. Gradient of f evaluated at this point p naught, or gradient of f of x naught y naught. Theorem: the directional derivative is a dot product. If f of xy is differentiable in an open region containing p naught, x naught, y naught, then derivative of f with respect to s in the direction of unit vector u at this point p naught, it is equal to gradient of f evaluated at p naught multiplied by unit vector u. The dot product of gradient of f at p naught with the vector u. So here we have directional derivative of f is equal to gradient of f times unit vector u. Find the derivative of f of xy. It is equal to x times e power y plus cosine of x times y at the point 2, 0 in the direction of v equal to 3i minus 4j. Recall that the direction of a vector v is the unit vector obtained by dividing v by its length. So here we have u equal to v over length of v, that is equal to v over square root of 3 squared plus negative 4 squared. So I use this part, and that is equal to v over square root of 25, and this is v over 5. So this means we're going to use what we have for v and then divide by 5. So this is equal to 3 over 5i minus 4 over 5j. The partial derivatives of f are everywhere continuous and at 2, 0 are given by. So here we have partial derivative of x at this point. This is equal to e power it is y. So based on what I have here, partial derivative of this y in respect to x, here we have e power y minus, then what I have here is cosine x times y. So partial derivative with respect to x, here we have y times negative sine x y valued at this point 2, 0. So this is equal to using 0 here for y, we have e power 0 minus 0 multiplied by what we have here on this part. This is 0. So we have this equal to e power 0, it is 1. Now partial derivative with respect to y at this point 2, 0, it is equal to x times e power y. So derivative of what we have here, it is e power y, and then derivative of power which is y, respect to y, it is 1. So here we have x times e power y minus x times sine of xy evaluated at this point 2, 0. So here we have x 2 times e power 0 minus x is 2. Then we have sine x times y, so it is sine 0, and sine 0 it is 0. So times 0, this is equal to 2 times e power 0, so this is 2 times 1, so that is 2. So the gradient of f at this point 2, 0, it is equal to I plus 2j. So here we had 1 times I plus 2 times j. The gradient of f at this point 2, 0 in the direction of v, it is equal to, based on what we had here for gradient of f, we have I plus 2 times j multiplied by unit vector u, which is 3 over 5i minus 4 over 5j. So this is equal to 3 over 5 minus 8 over 5, which is equal to negative 1. So based on what we did on the upward, the gradient of f times unit vector u, it is equal to negative 1. So here is over unit vector u, and here was gradient of f, which was equal to I plus 2 times j. And here was over p naught, which is 2, 0. Properties of the directional derivative. So directional derivative of f is equal to gradient of f times unit vector u. It is equal to length of gradient of f times cosine theta. So here the first one, we have the function f increases most rapidly when cosine of theta is equal to 1, which means that theta is 0. And u is the direction of gradient of f. That is at each point p and its domain, f increases most rapidly in the direction of gradient vector. So here we have gradient of f at p. The derivative in this direction, it is equal to length of gradient of f times cosine 0. So here cosine 0, it is equal to 1, and this is equal to length of gradient of f. Number 2, here f decreases most rapidly in the direction of negative gradient f. The derivative in this direction is length of gradient f times cosine pi. So cosine pi is equal to negative 1. So this is equal to negative times length of gradient f. Number 3, any direction you are talking to a gradient f not equal to 0 is a direction of 0 change in f, because theta then equals to pi over 2. So this is equal to length of gradient of f times cosine pi over 2, and this part it is equal to 0. So here we have length of gradient of f times 0. So this is 0. The direction which f of x, y increases most rapidly at this point 1, 1 is the direction of gradient of f at 1, 1. So this is equal to I plus j. It corresponds to the direction of steepest ascent on the surface at 1, 1, 1. Find the direction in which f of x, y is equal to x squared over 2 plus y squared over 2. Part A increases most rapidly at the point 1, 1, and part B decreases most rapidly at 1, 1, and part C, what are the directions of 0 change in f at this point 1, 1. Gradient of f at this point 1, 1, it is equal to xi plus yj at 1, 1. So this is equal to 1 times I plus 1 times j. So we have I plus j. Its direction, it is u equal to I plus j over length of I plus j. So this is equal to I plus j over square root of 1 square plus 1 square. And this is equal to 1 over square root of 2 times I plus 1 over square root of 2 times j. So in part A, we had a function increasing most rapidly in the direction of gradient of f at 1, 1. But here for part B, we have the function decreasing most rapidly in the direction of negative gradient of f at 1, 1. So which is using what we had in part A. Here u was equal to 1 over square root of 2 times I plus 1 over square root of 2 times j. Now here we have negative times u, so there's negative 1 over square root of 2 I minus 1 over square root of 2 j. Part C, the directions of zero change at 1, 1 are the directions orthogonal to gradient f. So find vectors n1 and negative n1 such that u dot n it is equal to u dot negative n it is equal to 0. These vectors n and minus n are directions of zero change. So based on this, n will have components negative 1 over square root of 2 and 1 over square root of 2, and negative times n is equal to, so here we have components of 1 over square root of 2 and negative 1 over square root of 2, which is same as writing n equal to negative 1 over square root of 2 I plus 1 over square root of 2 j, and for minus n we have 1 over square root of 2 I minus 1 over square root of 2 j. The gradient of a differentiable function of two variables at a point is always normal to the function's level curve through that point. At every point x naught, y naught, so we have this point here, in the domain of a differentiable function f of xy, the gradient of f is normal to the level curve through this point. So here we have our function f of xy, that is equal to f of x naught, y naught. So the tangent line to the level curve, partial derivative of f with respect to x of x naught, y naught times x minus x naught plus partial derivative of f with respect to y of x naught, y naught times y minus y naught is equal to 0. So we can find the tangent to the ellipse x squared over 4 plus y squared equal to 2 by treating the ellipse as a level curve of the function f of xy equal to x squared over 4 plus y squared. So find an equation for the tangent to the ellipse x squared over 4 plus y squared equal to 2 at the point negative 2, 1. The ellipse is a level curve of the function f of xy equal to x squared over 4 plus y squared. The gradient of f at negative 2, 1 is, so here we have 2x over 4, that is x over 2 I plus 2yj at this point negative 2, 1. So here instead of x, here we have negative 2, we have negative 2 over 2, that is negative 1 I plus we have 2 times 1, so there's 2j. Because this gradient vector is non-zero, the tangent to the ellipse at negative 2, 1 is the line. So based on what we have here, partial derivative of x naught, y naught, that is negative 1, which is this part here, times x minus x naught. So we have x and x naught, it is -2. So it is minus -2, that is positive 2, plus, then here for the square, the partial derivative of f with respect to y, it is 2 times y minus y naught, it is 1, and this equal to 0. So here we have negative x minus 2 plus 2y minus 2 equal to 0. So this is x minus 2y equal to -4. So this is our equation. Algebra rules for gradients. Number 1, sum rule. Here we have gradient of f plus g is equal to gradient of f plus gradient of g. Number 2, difference rule. Gradient of f minus g is equal to gradient of f minus gradient of g. Constant multiple rule. Gradient of k times f is equal to k times gradient of f, and k is any number. Product rule, gradient of f times g is equal to f times gradient of g plus g times gradient of f. And finally, quotient rule, gradient of f over g is equal to g times gradient of f minus f times gradient of g over g squared. So here on the square we have f of xy equal to x minus y, and g of xy, it is equal to 3 times y. Gradient of f is equal to I minus j, and gradient of g is equal to 3j. So in this part, we have gradient of f minus g, it is equal to gradient of x minus 4y. So here we have x minus y minus 3y, so this is x minus 4y. So based on what we have here, this is equal to I minus 4j and this is equal to, based on what we have here for gradient f, gradient g, this is gradient f minus gradient g. Because here we have I minus j minus 3j, that is equal to I minus 4j, which is what we have here. Now, here I have gradient of f times g, that is equal to gradient of, here multiplies x times 3y and negative y times 3y. Here we have 3xy minus 3y squared. So this is equal to, we have partial derivative of f with respect to x, I plus partial derivative of f with respect to y, j. So here the first part that we have is partial derivative of f with respect to x, and that is 3y, and then multiplied by I plus partial derivative of f with respect to y. So here we have 3x minus 2 times 3, so here we have 6y and times j, and f times gradient of g plus g times gradient of f, and is equal to, based on what is given here on this part, we have x minus y times 3j plus 3y times I minus j. So here I'm multiplying, and this is equal to 3xj minus 3yj plus 3yi minus 3yj, and this is equal to 3yi plus 3x minus 6yj, which is equal to what we have here on this part. Therefore, based on what we have here, gradient of f times g is equal to f times gradient of g plus g times gradient of f. So we verify this product rule based on this example. Find the derivative of f of x, y, z equal to x cubed minus xy squared minus z in the direction of v equal to 2i minus 3j plus 6k. And for part B, in what direction does f change most rapidly at p0, and what are the rates of change in these directions? The direction of v is obtained by dividing v by its length. So here we have length of v, it is equal to square root of, based on what we have here on this part. Here inside radical we have 2 squared plus negative 3 squared plus 6 squared. So this is equal to the square root of 49, and that is equal to 7. So direction of v, it is equal to, here we have u equal to v over length of v. So that is 2 over, here length of v, it is 7. So 2 over 7i minus, here we have negative 3, so that is negative 3 over 7j. Then we have positive 6. And then 6 over 7k. So here we're trying to find the derivative of f of x, y, z at this point p0 in the direction of v. So here we have the partial derivatives of f and p0. Here is a partial derivative of f with respect to x, that is equal to 3x squared minus y squared at this point 1, 0. So this is equal to, here we have 3 times 1 squared. So that is 3 minus 1 squared. So here is 2. And then we have partial derivative of f with respect to y. So this is equal to negative 2xy. At this point, 1, 1, 0. So this is equal to negative 2 times 1 times 1, it is negative 2. And partial derivative of f with respect to z, it is equal to negative 1 at this point. So this is equal to negative 1. The gradient of f at p0 is, based on what we have here, 2i minus 2j minus k. The derivative of f at p0 in the direction of v is equal to 2i minus 2j minus k times what we had for u was 2 over 7i minus 3 over 7j plus 6 over 7k. And here we have dot, so this is equal to 2 times 2 over 7, we have 4 over 7, negative 2 times negative 3 over 7, so this is positive 6 over 7, and we have negative 1 times 6 over 7, so here we have negative 6 over 7, and this is equal to 4 over 7. Now here part B, in what directions does f change most rapidly at p0, and what are the rates of change in these directions? The function increases most rapidly in the direction of gradient of f equal to 2i minus 2j minus k, and decreases most rapidly in the direction of negative gradient of f. So the rates of change in these directions are length of gradient of f, it is equal to square root of, based on what we have here, 2 squared plus negative 2 squared plus negative 1 squared, so this is square root of 9, and this is equal to 3, and negative times length of gradient of f, it is equal to negative 3.